Hello, welcome to this video on electrochemistry. Okay, here we go. Janet made me do this, and good for Janet. That's what. If this isn't enough, by the way, for any of you, please ask for more, or send me particular questions. Okay, so I just found these ones. I can find some more, but let's have a look at this. All right, so we've got to draw the standard hydrogen electrode to measure the electropotential of zinc. Okay, so if I want to find the electric potential, I've got to put a voltmeter there. There we go. That's the first thing we do. Try to make it neat and label it voltmeter. In here goes my hydrogen, H2 gas. It goes in at that temperature, and the pressure is 1 atmosphere. If you want to be clever, 10 to the 5 pascals. All right, there you go. I'm kind of working anti-clockwise here. So this has to have hydrogen ion concentration of 1 molar, 1 mole per decimeter cubed. Anything else? This is platinum. It's not zinc. Platinum, and it's often known as platinum black. And the black means there are very small particles. Okay, which gives it a high surface area, which the bubbles attached to. Going back up here, this is zinc, some sort of zinc ions, and the concentration of these guys must also be 1 mole per decimeter cubed. That's zinc. Oh, I forgot my salt bridge. And there's my salt bridge. And I think that's it. I can't think of anything else. If you can think of anything else, please let me know. Okay, zinc sulfate. Sorry, often we put in the salt bridge we put potassium nitrate. Okay, there you go, and that's to equalize the charge out on both sides, so current still flows. All right, so whatever you do, this is a must. This is not a joke. You must learn this. You must. This will come up in some description or another. You must learn that. Okay, so here's another one. This one's a bit more practical. Oxidation reduction reactions have a variety of uses. We're making a voltaic cell here just for revision. A voltaic cell. This gives us electrical energy. Electrical energy. Okay, in other words, it gives out electrons. So what am I talking about? I'm looking at another screen and I'm getting confused. It gives out energy, so this is exothermic, isn't it? Okay, it's where we make our batteries from. The other type of cell is electrolytic cell. Now this takes in electrical energy. Electrical energy goes in, so these guys are endothermic. All right, now at the top of a voltaic cell, you're going to see a voltmeter. At the top of an electrolytic cell, you'll see a power source. Okay, because one gives out energy, one takes energy. Very simple as that. So let's draw the annotations here. What color shall I use? Let me use quite a dark color, that color. This thing's going to be our voltmeter. Obviously, now I don't know which metal is going there or there yet. We'll figure that out from up here. We're doing aluminium. Let me try to draw that as neatly as I can. It's aluminium against tin. All right, now I know that aluminium is more reactive than tin. But do you know that? Well, let me show you how you should know it. Let me see. There we go. Right, I'm going to have to copy this and show you. Oopsie daisy, what have I just done there? Right, screenshots, and let's have a look. There's aluminium and there's tin. All right, copy that. Now I'm going to push this up. Actually, I'm going to push it to the side. Excuse me, I've got a sore throat. There, for some reason it's not showing. There is page 24. And that's the electropotentials. Okay, so let's make them nice, like that. Now, what do they mean then? Right, the more positive The more positive the number, let me get a nice pen. And again, please ask me questions on this. The more positive, it means it's going to go that way. In other words, it takes in electrons more easily. So the more positive takes in electrons more easily. Okay. Now the other one, if it's more negative, all right, that means it doesn't want to go this direction more. Let me change that. If it's more negative, it would rather go that direction. The more negative it is, and that means it gives out electrons. Gives out electrons more easily. Okay, so if you've got metals, the more positive one, which one is the more positive out of these two? This one. That one, the tin system, okay, that thing, the tin, is minus 0.14. And the aluminium system, this, Al3 plus 3 electrons, gives me, where is it? Minus 1.66. It may, that's wrong, isn't it? Get rid of that rubbish, aluminium. It means, and that's 0.166. Oh, it's not. Sorry about this. This is minus 1.66 volts. And I don't know what that says now. 0.14, I think, yeah. Okay, of these two, aluminium is more negative, all right? And that means it has a greater tendency to go that way. Okay, tin, therefore, is less negative and will have a greater tendency to go that way. So which one gives off electrons more easily? Well, obviously the aluminium. So therefore we can say the aluminium is more reactive because it wants to give off electrons more easily. Okay, so knowing that now, we can answer this bit. It shows us which way the electrons go. And since aluminium is more reactive, it will give off its electrons more readily than the tin. So this is the aluminium side, and this is going to be the tin side. These electrons are going to go from the aluminium to the tin. So how do we know that? This one is going to be the more negative, and this one's going to be the more positive electropotential. Okay, we can get rid of those question marks now. There and there. Okay, so let's continue. What's this? Well, these are aluminium ions, aren't they? Aluminium 3 plus aqueous. And it's actually told me what they are. They're aluminium nitrate. So maybe I should have written that. Whatever the aluminium concentration, the aluminium ion concentration must be 1 mole per decimeter cubed. This guy is, what is it? This is tin nitrate. Tin nitrate, badly drawn, but you know what I mean. And again, the concentration of tin ions must be 1 mole per decimeter cubed. All right, this thing is our salt bridge. Okay, so write the overall equation. Well, you wouldn't do this in an exam, but I'm showing you how I would do it. Okay, now the equilibria is this, isn't it? Al3 plus 3 electrons gives us aluminium. This is before you connect them, if you like. Before connection, there's an equilibrium set up. On the right-hand side, you're going to have Sn2 plus 2 electrons gives you Sn. So these are the equilibria. Let me try and draw an equilibria. There you go. These are the equilibria before. This is aluminium. That looks awful, doesn't it? This is before you connect them. Now, since the aluminium is more negative, which we can see, let me show you up there. Nice color there. Aluminium is more negative, okay, and the tin is more positive. That means the aluminium will give up electrons. And the way I've written it there, the left to right, it's going to take in electrons. So therefore, this one must be this way, the other way around, right to left. So this is aluminium is going to, this is after you connect them. After connection. So aluminium is going to give aluminium ions, plus 3 electrons. And the tin is going to suck in the electrons, so that's going to stay as it is. Okay. Now we've got to add these two together, but before we do that, we must be cognizant of the electrons don't balance. There's 3 there and there's 2 there. So I've got to balance them before I add them. Trust me. You think you can add them and then balance them. It's a pain. Don't. Balance them before. So I'm going to this side by 2, and that becomes 6 electrons. This side by 3, 6 electrons, and 3. So now when I balance them, the excuse me, the electrons are going to cancel out. And now let's do that. All right, so this is going to become 2Al solid plus 3SN2 plus aqueous gives me 2Al3 plus aqueous plus 3SN solid. Actually, it's not many marks for that because it's harder than it looks, but there you go. There's only 1 mark. And there's 3 marks for the easy one, so there you go. Calculate the cell potential using section 24 of the data booklet. All right, here we go. So let me write these nicely. I've got the data booklet in front of me, and it's over there. I'm using this thing. So where's aluminium? Aluminium, Al3 plus. Aluminium system that has a potential of minus 1.66 volts. That's E equals. And the tin system, SN2 plus, SN has an E electrode, I should say, make it correct, of, where is it, minus 0.14. Okay, now, this is how you work them out. The E cell is E electrode minus E electrode. Now you're thinking, what the hell was that? All right, and then I'll put the standard signs on all of them. Now, E electrode minus E electrode, it is, and I hope you remember this, let me get a nice color. This is the more negative. All right, and this one is the more positive. Okay, now, how else can you say that? You could say the E electrode is the one that gets oxidized and the one that gets reduced. The more negative is the one that's going to get oxidized, and the less negative is the one that's going to get reduced. I just remember it's the more positive minus the more negative. So let's write these in. The more positive is this number, 0.14, minus the more negative, which is this number, 0.166 volts. And where's my calculator? Okay, so that is minus 1. Sorry, what am I doing? Sorry, I'm all over the place today. 0.14 plus 1.66, and I get 1.52. So I get positive 1.52 volts. Okay, hope that one makes sense to everyone. Now we've done that bit. Let's have a look at that. Calculate the Gibbs free energy. Now, I don't know if it's a trick, something you should know, I guess. This is positive. Once we've done the cell potential, we've given it a positive number. So this must be simultaneous. Simultaneous. In other words, it's going to go. All right. So therefore, if we work out the Gibbs free energy, the Gibbs free energy for one such as this must be negative. So the Gibbs must be negative. So if we get a positive answer, we've done it wrong. Okay. Now, so I hope that makes sense. Now, what is our formula for this? Let me see if I can squeeze it in here. It is delta G equals minus NF E cell. Not C electrode, C cell. E cell, not so is that number. All right, so delta G is minus the N is the number of electrons in the equation. Okay, so where's the equation? There's a sharing, as you can see here. I've messed it up there, and there. There's a transfer of 6 electrons, so we put minus 6 there. Okay, so that's minus 6 times Faraday's constant, 96,500. I think it's either 96,5 or 95,6 times 1.52. Okay, what does that give me? Well, it's going to be a negative number, isn't it? Because the cell potential is positive. So 6 times 96,500 times 1.52 gives me, oh, got a big number, 808,000. 808,080. All right. Now, the units of that are going to be joules per mole. Okay. And obviously, you can chop that up into minus, don't forget the minus, 880 kilojoules per mole. But when you use this, remember this, the answer is going to be in joules per mole. All right, not kilojoules per mole. Basically, if you get a huge number, it's going to be joules. That's how I remember it. Now, what's interesting about this? Well, look at this. It's a big number, that. This is big. So therefore, this will be very spontaneous. Spontaneous. In other words, it is very feasible. It will happen. Okay, all right there. Now, I've got some multiple choices now. I didn't want to make this too long because I want to make sure you engage with it and then ask me if you need help. Okay, and that's the most important thing. I've just got, I can see on my other screen here, I've just got an email from a Form 5 student asking me stuff, all right, and I expect you to do the same. All right, they're asking, I don't know what they're asking about, but I'll read it later. Let's try and do these multiple choices because, as you know, these are going to happen. You're going to get them. How many do I have? All right, and there's one there. So let's take this one, copy that, and push it up there. All right, make it 100. That's way too big. Make it small. There you go. Any more? Do I have any more? Oh, I do. Oh, there's another one. We'll do another one in a minute. Right, I don't know how many minutes we've done so far, but I don't want to be doing this for too long because we'll get bored. Products of the electrolysis of molten potassium chloride. That's a Form 5 question, isn't it? It's easy because it's molten. So you've got potassium chloride, so you've got potassium ions and chloride ions. Potassium ions are going to go, because they're positive, they're going to go to the negative. Okay, they're going to go to the cathodes. So I'm going to get potassium there. So it's one of these two. And this one's going to go to the anodes. All right. So I'm going to get chlorine gas. It's the product. So it's that, isn't it? So the answer's B. Very easy. What would the potential be if that now it's used as the reference standard? I don't quite follow this at the moment. Let's have a look. Of that, half cell is used as the reference standard. I guess you're doing it. It's the electropotential. So of the manganese and system, if half cell if is used as a reference standard, I don't quite understand what they're getting at there. I guess it's just the cell potential. Electrodes. Oh, if we're using that, I see. That's a strange question, but I think I get it. All right, let's do what we did before. All right, let's look at these two. Which one is the more negative? It's that one. So the E cell, I'll explain that in a minute. The E cell is the less negative, minus the more negative. I hope that makes sense. So hopefully there's an answer here. So 0.77 plus 1.18, and I get 1.95 plus 1.95. All right, so I get that. So that's the E cell, 1.95 volts. But it's also if you regard the this one, the Fe2 plus Fe3 plus system, okay. If you think of this as the standard, all right, if that's the standard, it's also the E electrode. All right, it's a funny way of asking it. It just confuses things, really. All right, so it's the electropotential if you're saying one of them is a standard, and then it's also the cell potential if it's not a standard. It's just a semantic thing, really, that. So that's plus 1.95. Okay, I hope we're good with that. There we are. What happens to the mass of each of the electrodes when aqueous copper sulfate is electrolyzed? Well, again, this is Form 5 stuff. What happens is, if their electrodes are made of copper, all right, the anode, there's the anode, and the cathode here. This is the anode, and this is the cathode. All right, ions go into solution from the anode, and they go on to the cathode. So the cathode actually gets coated, and the anode loses mass as it goes on. All right, interestingly, the solution color is blue, and it stays blue because for every ion that goes into solution, one ion goes out of solution. So basically, the concentration of copper ions remains constant. All right, just a silly thing, nothing to do with this question, but that's why it stays blue. So the anode, where's the anode? The anode loses, so it's one of these two, and the cathode gains, so it's that one. So the answer is C. Okay, a nice straightforward question. Now, Form 5 question. Now, let's have a look at the next one. All right, here we go. All right, outline how catalyst increases the rate of reaction. Well, how does it do it? It provides an alternative pathway, doesn't it? So these two things you must say, not one thing, two things. It provides an alternative pathway for the reaction. Now, this is the big point, which has a lower activation energy, which I'm sure you all know. Okay, activation energy. All right, so if we were to draw that, let me draw it nicely very quickly. Oh, what the hell's that? That's weird, isn't it? All right, so why didn't that work? There, it worked. Oh, that didn't work then. All right, let me just draw it. Is that going to work? No. Strange. It used to work. All right, let's draw a line down there. Wow, that's weird. Why isn't that working? Oh, it's shift it needs. Okay, I thought it was control. Shift straight down there. There. So you get your reactants and your products. I'm just doing this, but you should all know this. That is obviously the activation energy. But if you have a catalyst, it lowers the activation energy. There you go. So it lowers the activation energy. So this is EA, and this one would be called EA cat. Don't forget, it lowers the activation energy for the reverse reaction as well. That's why catalysts don't alter the equilibrium. Equilibrium remains unchanged. All right, a bit of physical chemistry there for you. Why does increasing the temperature increase the rate? Right, well, there's two reasons here. Number one, I think the nice, easy answer is it will increase the molecular collision frequency. Okay, a molecular collision frequency increases, and I learned this term. It's a nice thing to learn. Molecular collision frequency increases. In other words, everything gains potential energy, doesn't it? What am I talking about? Potential energy. It gains. What does it gain? It gains kinetic energy. All right. Higher temperature gains kinetic energy. Kinetic energy increases. Okay, which leads to a greater molecular collision frequency. And the other one I'd say is a higher proportion of molecules, reactants have energy greater than or equal to the activation energy. All right, I think that's your 2 marks there. All right, I hope so anyway. All right. If they're not, if you want to argue, go for it. I love arguing, seriously. Makes me realise you're engaging. All right, there we go. What's this? Let's have a look at this. Copy this down, paste it there. All right. Discuss referring the integral fluids presence, the relative volatilities of that and that. I think I've done this recently. It feels as though I've done it recently. All right, now let's draw the structures of them. All right, let's do it in red. Where are we? Propanone. Looks like this. CH3. Oops, that's not right at all. CO. CH3. And there is a dipole there, isn't there? I'm sure you can see it. Delta plus and delta minus. So the intermolecular forces here, the IMFs here, you can't cheat, you can't say IMFs, I can. The IMFs here are permanent dipole, permanent dipole, permanent dipole, permanent dipole. Okay, but in ethanol, is it ethanol? It's propanol. In propanol, you have this 1, 2, 3. CH3, CH2, CH2, OH, and you've got, that's not right, you've got an H, and then you've got that, CH2, CH2, CH3, and obviously there's a dipole here. You've got to draw the lone pairs there. Okay, what a nice color can I use? I'm going to use green for a while. All right, so this is delta minus, delta plus, delta minus, delta plus, and there's going to be an intermolecular force there, which is also permanent dipole, but this is given a special name because there's some magic here. These are called hydrogen bonds. Okay, and this isn't for 3 marks. That's not enough, I think. What I've written there. Now you've got to say, well, hydrogen bonds are more strong, greater than, stronger than the dipole-dipole interactions. The dipole-dipole interactions, which you've got to say. You've got to mention this. It's maybe obvious, but you've got to mention it. So the hydrogen bonds are greater or stronger than the dipole-dipole interactions. Therefore, the volatility of propanone. Now, volatility means it's going to form a vapor more easily. So the volatility of propanone is greater than, where is it, propanone? Propan-2-ol, because less energy needed to escape the liquid because of the intermolecular forces, because of arguments up here. Now, it's easy to get 1 mark in this, it's easy to get 2 marks, but please, I beg you, try and get 3 marks. Eh? So this, even though it looks relatively easy, it's also easy to lose marks here. So I've explained the bonding very clearly. I hope I have anyway. I've explained to you which one is stronger. And then, again, you might think it's obvious, but you've got to say, and therefore it takes less energy to do this than it does that. And you've got to mention that. You've got to. All right, no excuses. All right, next one. I hope I didn't mean this to be this long, but here you go. All right. Whoops, daisy. All right, where are we? Push that there. Okay. Oh, I have to sneeze. Right, here we go. I've got to get my my thing up again, haven't I? My electropotentials, because I've got to figure out which one, lead or nickel, is on the left-hand side. Well, it's the more reactive one, so it's going to be the one with the lower potential, isn't it? The lower electropotential. So let me see if I can find them. Where's lead? There's lead. I found lead. Okay, let me take a screenshot for you. What's the other one? Lead and nickel. Oh, they're on the same page. That's good. Whoops, daisy. Get rid of that. Start again. Screenshot nickel and lead. There we go. Stick it over here. Much too big. Okay. Now it's too small. All right. Oh, we're much too small. All right. Oh, hold on. The recording's going to end here because I'm up to 30 minutes.